Hello everybody, welcome to our video today where we're talking about biochemistry chapter 2, enzymes. Da-da-da-da. So let's get started. First, let's talk about what is an enzyme. So here we go, sorry, up here, an enzyme. Perfect, kind of. Okay, an enzyme is a biological catalyst, okay, that remains, does not get taken up in the reaction, and it does not change delta G, okay, or the equilibrium. It only changes the rate of reaction. That's definitely an important point to remember. And the enzymes also can stabilize the transition state, which means they can lower the activation energy required for the reaction to proceed, which is hence how they increase the rate of reaction. So first, let's talk about the types of enzymes. So I'm hoping you can see that. Okay, so first we have these types of enzymes. So we have oxoreductases, which are involved in the transfer of electrons in redox reactions. Okay, so they transfer electrons so that a redox reaction can occur. Then we have transferases, and those move functional groups from one molecule to another, okay, to catalyze a reaction that way. Then we have hydrolases, which catalyze the cleavage of a molecule with the addition of water. So by adding water, hydrolases are able to cleave a molecule. Then we have lysases, which catalyze the cleavage without the addition of water and without the transfer of electrons, okay? So transferases, hydrolases, and lyases are a cleavage without these two things. Then we have isomerases, which catalyze the interconversion of isomers. Then we have ligases, which join two biomolecules, which we'll get into in another biology chapter when we're talking about DNA replication and things like that. So those ligases join two biomolecules. Then we have lipases, which catalyze the hydrolysis of fats. So it's basically taking a fat into a fatty acid, a glycerol, or an alcohol. Okay? And then we have kinases, which adds a phosphate group. Okay, which a kinase is a type of transferase. It's just a more specific one because it is adding a phosphate group from an ATP molecule. So adenosine triphosphate, a kinase is going to take one of those phosphates off that ATP molecule. Then we have phosphatases, which actually remove a phosphate, which is also a type of transferase. So you're removing a phosphate. And then we have phosphorylase, which is different than a kinase because a phosphorylase introduces a phosphate group to an organic molecule, not from an ATP, and typically to a glucose molecule. Okay, so typically introducing a phosphate group to a glucose molecule would be a phosphorylase. Okay, so now that we've gone over some of the types of enzymes, I know those are a lot of words, and sometimes the words in them, can help you determine their function, right? So transferases, transfer, oxoreductase, redox reaction, things like that, isomerase, isomers. So a lot of those you can just kind of learn that way, but it's definitely important to know those. And you're going to see a lot of kinases, so make sure you know that one as well. So next we're going to talk about the saturation kinetics, and I'm hoping you can still see this. We will move it down a little bit to there for now. Okay, so next we are talking about saturation kinetics. So basically with saturation kinetics, as you increase the concentration of substrate, you're going to increase the rate of reaction until the max value of saturation is reached. So if you look at this graph over here, you have this is a Michaelis-Menten plot, okay? And this is the okay, like velocity, and then we have S in these brackets means substrate concentration. So if you're looking at this plot right here, this dotted line is called the Vmax, okay? And this point right here is called the Km, and we're gonna go into what those mean in just a moment. So in this Michaelis-Menten plot, you can see that as you're increasing the substrate concentration, right? You're increasing the substrate concentration, the rate of reaction is increasing as well, which is why you get this curve right here until the max value is reached. So as soon as you get to this Vmax, it doesn't matter how much substrate you're adding, you are not going to increase the rate of this reaction because it's already saturated. So the Vmax is when all of the sites are saturated. So this is relative to enzymes and substrates, okay? And then we also have, as we said, the Km. And the Km is going to be this substrate point right here because Km is the substrate concentration where the enzyme is at half of its Vmax. So to find the Km, all you have to do is find the Vmax, find half of Vmax. See, it reaches the Vmax. It continues to be on the Vmax here. But at this point right here is kind of where it reaches its Vmax. So you're going to look at where it gets to the Vmax, find half of that, okay, on the curve right here, and you're going to find the substrate concentration in which this occurs. So you're looking at this x-axis. So that is important because these are in, some type of relationship, and we're going to get into that when we look at these types of inhibition. But before we do that, we're just going to look at these two equations right here. So this equation is the Michaelis-Menten equation, and you're looking at this to say, just explaining it in an equation what we were saying in words. So basically you have the enzymes plus the substrates become the enzyme substrate complexes together to produce enzymes, okay, right, because they're unchanged in the reaction, and the products that you desired. So that's just in an equation what this all kind of represents. But another equation is this right here. So this is saying that this is the Michaelis-Menten equation, and it's saying that this isn't necessarily the Michaelis-Menten equation, but this equation relates to this Michaelis-Menten graph. So we have V naught, okay, so a V value equals, so this is the speed of the reaction, equals the Vmax times the substrate concentration divided by the substrate concentration at this, at this V value plus Km. So these substrate concentrations dictate the speed of the reaction at that point, okay? So these substrate concentrations are subject to change depending on what point you're looking at. So if you want to know the speed of the reaction here, you're going to look at, okay, what's the substrate concentration right here? Oh, it's this? Okay, I'm going to input that here and here, and I'm going to, the Km and the Vmax. But you just add those by looking at the graph or the other information that's provided. It depends. I believe that is all for this. I know it can be a lot, but don't be afraid to rewatch the video or slow it down so that you really understand what this graph is showing you and the concept behind this equation. So slow it down, rewatch it, but yes. So another important part to this, I hope my shadow's not covering it. So another important part to this is the types of inhibition. So we're looking at 3 types of inhibition. There's also mixed inhibition, which I do not have drawn here, but these are the 3 main types of inhibition. So first we have competitive inhibition, and the reason we're talking about inhibition is because we're talking about enzymes and substrate, and there are inhibitors that stop the substrate from getting to the enzyme, right? So we have competitive inhibitors, and competitive inhibitors bind to the active site. That is very important to remember. So competitive, they're competing for the spot at this active site. So the substrate and the inhibitor are competing to bind at this active site, okay? And with competitive inhibitors, the Vmax does not change and the Km increases. So what I mean by this is just because there's a competition of getting to the active site first, the maximum can still be produced. The Vmax does not change, okay? You can still produce this maximum up here, but in order to do that, that means your Km is going to have to increase. So if you increase the Km, your graph is going to kind of look a little more like that, and it's going to appear just underneath our original one because you're increasing the Km. If we're increasing the Km, that means you need to increase the substrate concentration, okay? Because it's going to take more substrate to get to the Vmax because there's that competition. So if you add a lot more of your desired substrate, the chances that your desired substrate are going to get to the enzyme before the inhibitor is better than if you had less substrate, right? So that is for competitive inhibition and just conceptualizing why the Vmax doesn't change and why the Km will have to increase. And with these types of inhibitions, each of them come with one of these Lineweaver-Burke plots, okay? And what this tells us, you can also see the type of inhibition. So this y-axis right here in a Lineweaver-Burke plot represents 1 over Vmax. And this x-axis here represents -1 over Km. And for me personally, it took me a long time to like really understand what those values mean, but I found it more helpful to just say, okay, this y-axis is in relation to the Vmax. It deals with the Vmax. If we're talking about Vmax, it's going to be this y-axis of what we're looking at. And then this x-axis is in relation to the Km. So that is how I'm able to understand this. So when we're looking at a graph like this, the dotted line is just our natural, our natural line without any inhibitors. So if we look at this right here, we said competitive inhibition, the Vmax will not change. So if the Vmax does not change, that means that on this y-axis, the point which represented the Vmax, that represented the Vmax is not going to change, which means if you have this dotted line and you have the straight line which represents the competitive inhibitor, they're going to still cross that axis at the same place that is in relation to Vmax as a whole because the Vmax does not change, okay? Now, if we're looking at the Km needs to increase. And because this is an inverse graph of just regular Vmax and Km, when you say the Km is increasing, it's actually going to be closer to 0 because if you look at a graph like this, right, this side is negative and this side of that x-axis is going to be positive. So if the Km is increasing, that means that the Km will go closer to 0, which is why you have this solid line closer to 0 than the original dotted line that did not have a competitive inhibitor, okay? So I know that was a lot, but I tried to explain it the best I could. But again, rewatch it until you really hear like the words and you can understand what this graph is representing. So next we have down here, we are showing non-competitive inhibition. So with non-competitive inhibition, that is when the enzyme binds to an allosteric site. Okay, and an allosteric site is at another point on the enzyme that is not the active site. Okay, so we can see this here. This is our inhibitor right here. So it is binding to an allosteric site so that when the substrate actually binds to this enzyme, it's inactive. Okay, so in non-competitive inhibition, the Vmax decreases because you're making this enzyme unavailable. So the amount of product that you can produce actually reduces. Okay, before it was just competitive, but here you're actually decreasing the maximum that you can produce by making this unavailable here. So we have Km that does not change in this case because if you look at this graph that we have, again, the Lineweaver-Burke plot, you can see that the Km values, remember, which is in relation to this x-axis, is stemming from the same place, but the Vmax value is decreasing, okay? And because it's an inverse plot, that actually means that it will be above the original line. And although that may be confusing to grasp, how I understood it was, okay, if the Km has no change, that means that they're going to stem from the same point on the x-axis. And I recognize that the Vmax has to decrease. Since it's an inverse, it's going to be the opposite of what I think. And instead of, decreasing as I would really recognize it, of going down, it's going to actually decrease but be represented above the original line on a Lineweaver-Burke plot. Okay? A lot of the time you can just recognize it, and honestly what I did was just to say, okay, the Km doesn't change, that's easy. I know it's going to be, they're going to stem from the same point of this x-axis, and I know the other types of inhibition don't necessarily do that, so that's easier for me to recognize this as non-competitive inhibition, okay? But just, to recognize the properties and the circumstances of this inhibition is important. So like we said, for non-competitive, it's going to bind, the inhibitor is going to bind to an allosteric site, and the Vmax is going to decrease because you're rendering this enzyme, inactive. And the Km will not change. Okay, the substrate that it takes, the amount of substrate that it takes to get to half the Vmax will not change in this case. Okay, so finally on to our third type of inhibitor or inhibition. We have uncompetitive inhibition. So with uncompetitive inhibition, you're going to see that the inhibitor only binds to the enzyme substrate complex. So the enzyme substrate complex is once the substrate and the enzyme are bound together. So the in uncompetitive inhibition, the inhibitor will bind to the enzyme substrate complex as a whole. In this case, the Vmax decreases and the Km decreases. Okay, and this one, I just, it's easy to remember, they just both decrease for uncompetitive inhibition. So you need to be able to recognize all of these things, honestly, in terms of the Lineweaver-Burke plot, but also in terms of the properties under each. So to know that, okay, competitive inhibition, Vmax no change, Km will increase. Non-competitive inhibition, Vmax decreases, and Km has no change. And then finally, for uncompetitive, Vmax and Km both decrease. Okay, so because the Vmax in this case is going to decrease, the Km that it takes to get to that Vmax is also going to decrease because it's looking at the substrate and the enzyme when they're already bound together. And that's the difference between these two, is that here the Km doesn't change, but here the Km also decreases because they're already bound. In this case, they're not already bound. So there's no change in the Km. But here, because you're using a piece of a substrate and the enzyme together, they're both going to decrease in terms of the Vmax and the Km. And when you look at this Lineweaver-Burke plot, they are actually parallel. So that's another easy one to just recognize. Uncompetitive, they're just staying, I visualize it as them just staying in their own lanes. They're uncompetitive with each other. They're just parallel, okay? Because they both decreased. Okay, so that I would say was definitely a lot. I know it took me a minute to really memorize all of those things. But now we're getting into a little bit of the lighter part of the chapter, I would say, and we're just looking at a couple other important parts of enzymes, but are, in my opinion, easier to conceptualize. So we have the activity of enzymes. So we have a lock and key theory, and in this theory, the enzyme and the substrate are exactly complementary. Okay, so you have this and you have this, and they're exactly complementary. They fit directly with each other. That's it. But what we really came to find was that the induced fit theory is a better representation of what happens, because the enzyme and the substrate will undergo conformational changes to interact with each other. So what that means is, instead of being so stiff, if they see, this substrate coming and this is the enzyme, they'll kind of both undergo conformational changes so that they can interact with each other. So instead of it being, oh, look, it doesn't fit, it's going to be, oh, it's here. Okay, let's conformationally change so that we can interact with this substrate. Okay, so that is the induced fit theory. Important other things to note of enzymes. So you'll have cofactors, which are metal cations that are required by some enzymes to function. So those are cofactors. Then you have coenzymes, which are actually the organic molecules that are required by some enzymes to function. And with these two, it's important to remember that they will bind to the active site so that they can participate in the catalyzation, in catalyzing, okay? Then you'll have apoenzymes, which are enzymes without cofactors. They don't need them. And then you have haloenzymes, which are enzymes that are already containing their cofactor. So there's, again, some vocab to know. Then we have effects of local conditions. So definitely the environment can affect how enzymes function. So temperature definitely can affect how enzymes work. A lot of our enzymes are meant to perform at a body temperature. So if you just took them out of our body and put them in a freezer, that temperature isn't conducive to the enzymes performing their functions. Okay, so temperature has an effect, and so does pH, because pH can easily denature a lot of enzymes if they're not meant for a pH that you put it in. So normally enzymes work at a pH of 7.4, but there are some enzymes that work in our stomach, which are way more acidic, and those have a pH threshold that is much lower because they are meant to function in acidic environments. So it really is depending on the type of enzyme, but temperature, pH, those can affect how an enzyme works. And then also salinity, because salt can disrupt the ionic and hydrogen bonding of enzymes. And we know bonds, is really what makes all of this work. So salinity, pH, and temperature play a role, okay? So then we have regulation of enzymes. So we have feedback inhibition. A lot of this we might have heard about before, but we have feedback inhibition, which is when you have a chain of like a pathway, and one of the products is produced excessively, and that product will actually come back to a stage earlier in the pathway, and which is the feedback, and actually inhibit the pathway from continuing because enough product was already produced. Then you have reversible inhibition, which is when you replace an inhibitor with, so let's say there's an inhibitor with this enzyme, right? But I have something else that needs to go in this space. You're going to replace an inhibitor with a compound with a higher affinity. So if this right here is if this substrate right here is in this enzyme, right, and it has an okay affinity, if you want to take this out, you're going to have to replace it by something with an even greater affinity to the enzyme, okay? Or, something with a greater affinity of the substrate. So the substrate is okay here, but if you put something with a super, super strong affinity to the substrate nearby, it's going to, remove itself from the enzyme and go interact with the other compound that you just introduced because it has a higher affinity for that compound. So that is a reversible inhibition. So that's, how you can replace the inhibitor in an enzyme. Then you have irreversible inhibition, which actually alters the active site so that this enzyme is permanently unavailable. That's why it's irreversible. It changes the active site. It does something to it that you just can't come back from, and that enzyme won't be able to be used for what it was meant for because this irreversible inhibitor affected it. And then we have suicide inhibitors, which are substances that are analogous to the it's a substrate analog that covalently and irreversibly binds to the active site. So you know how you were saying before, you could, take something with a higher affinity to remove it. Sometimes a suicide inhibitor is just going to stick with this enzyme and it covalently, and it's just going to be irreversibly bound to this active site. Let's see what else we have here. So we have allosteric effectors, which we've kind of touched on before, but allosteric effectors bind to an allosteric site, right? So that's a part of the enzyme other than the active site. And it will induce a conformational change of the enzyme so that the substrate can't bind, okay? And so this displays cooperativity, and it does not obey the Michaelis-Menten plot that we talked about earlier. And what we mean by this cooperativity, so you can have a T, okay, that it can be in a tense state, which means it has low affinity, or it can be in a relaxed state that has high affinity. And what by cooperative binding, what we mean by this is that heme is a good example. So hemoglobin has 4 subunits in it, right? And we'll go into that in biology. I believe circulation chapter might be chapter 6 or 7, but hemoglobin, right, carries this oxygen through your body. And so what hemoglobin has is cooperative binding, which means when one of the subunits, when one of the oxygens bind, that makes it easier, and the other oxygens have a higher affinity. And when that second oxygen binds, the other oxygens have a higher affinity too, and it's easier bound than the first one. And then finally the fourth one too. So that's cooperative, positive cooperative binding. And you also have negative cooperative binding, which means that if once one of the things is bound, it is more difficult for the second thing to bind. And when those two things are bound, it makes even more difficult for the third thing to bind, and so on. So that would be negative cooperative binding. So what this means in terms of numbers is you can look at Hill's coefficient. So if Hill's coefficient is bigger than 1, that means you have positive cooperative binding. If Hill's coefficient is less than 1, that means you have a negative cooperative binding. And if you have Hill's coefficient equal to 1, that means you have no cooperative binding. Okay? Another thing that I didn't write down, but was just some of the vocab in this chapter, was a homotropic effector is allosteric regulation that is also the substrate. And then you have heterotropic effectors, which is an allosteric regulation where the molecule is different than that of the substrate. So the molecule that binds is different than the substrate in the allosteric regulation. So those were just 2 terms that I had seen that I thought were important. Okay, and now we're into our final part. Thank you for staying with us for this long video. But I think hopefully we've covered all the major topics and that you have a better understanding of what goes on here. But we just have one more thing to go over, and that is Kcat. So Kcat is actually the catalytic efficiency of an enzyme. So Kcat measures the substrate molecules that have turned over into product. And there's actually an equation that goes with it. I'm going to take you over here so you can see it. So this equation is V equals Kcat times the enzyme concentration times the substrate concentration over the Km plus the substrate concentration, okay? And this equation is important because it shows you the relation between the Kcat and the km, and the speed that the the reaction will proceed. So this really all means that if you have a high km, so if this numerator up here, right, is high, and you have a low, sorry, if you have a high kcat, I hope I said that. If you have a high kcat in this numerator, and you have a low km, that means that you will have a very effective enzyme because V will be high because you have a high numerator and a small denominator. So that's just putting all this in relation. I believe we cover this in another chapter. We talk about rate of reactions, but it's important for this chapter to know that this represents kcat is the catalytic efficiency. Okay, and that is everything for now. Thank you so much for staying with us in this video, and I hope you learned something. If you have any comments, questions, please put them below. And if not, as always, I will see you in the next video.